going to start out by reviewing delocalized electrons and resonance. So first, let's just think about what delocalized electrons are. Delocalized electrons are electrons that are spread over 3 or more atoms, and when you have delocalized electrons, you're going to end up with resonance structures. So the difference is electrons spread across the molecule being delocalized, or electrons being localized on a single atom of a molecule. Let's take, for example, these two structures. Here we have a pi bond next to a positive charge, and here we just have a pi bond with no positive charge in the structure. In the structure on the right, these pi electrons are localized between these two atoms. In the first structure, however, because of this positive charge, these pi electrons can delocalize. And the reason is because you can think of this positive charge as an electron vacancy on the carbon. This carbon wants electrons, and it just so happens the neighbor has electrons that it can donate. And what we can draw here is a resonance structure. We'll move those pi electrons over here, shared between the central carbon and this carbon that had the positive charge. But since we took electrons out of this carbon on the left, that carbon now bears a positive charge. Here, the pi electrons are shared between 3 carbon atoms. Or another way of saying that, the pi electrons are delocalized over 3 carbon atoms. Just keep in mind, though, that neither of these two resonance structures actually exist. These are not individual distinct structures. They help us in our understanding, but really there's one true structure that is a resonance hybrid. In the resonance hybrid, what we have is effectively the pi electrons distributed between the 3 atoms, as well as that positive charge spread throughout the 3 atoms. And what that does is it helps to stabilize this electron vacancy here. As opposed to one carbon being electron deficient, it spreads that deficiency across the molecule. Now let's tie this into an understanding of p orbitals. All right, the first point is that every carbon that's part of a pi bond has a p orbital. So that's going to be easy to pick out. The second point is also pretty easy. Carbocations are in p orbitals. The third point is the one that will give us a little bit of trouble and takes a bit more reasoning, has to do with lone pairs and carbanions. Sometimes they're in p orbitals. And we're going to spend some time looking at how to figure that out. All right, but let's go back to an allylic carbocation structure. So that's what we have up here, is a simple allylic carbocation. And I'm going to draw another one. This one's just a slightly longer chain, but using these points made above, let's draw a picture of this represented with p orbitals. When we do that, you want to start with your sigma bonding framework. So that's just a 4-carbon chain. Next, what you want to do is draw in p orbitals everywhere you have a double bond. So this carbon will have a p orbital because it's part of the double bond. This carbon will have a p orbital because it's part of the double bond. Next, we have a carbon that has a positive charge. We can go ahead and draw a p orbital on that. And what you can even do, just to make sure you know that there's a positive charge there, a lot of times we'll just write the plus in one lobe of the p orbital to represent the carbocation. What we find here is a conjugated system. Anytime you see 3 or more p orbitals in a row without any breaks between them, that's a conjugated system. Okay, so let's look at another molecule here. It has a lot of similar features in that we have double bonds and positive charge. And the question is any portion of the molecule conjugated? So let's draw a p orbital picture for this. Again, stick with your same sigma framework as in your original molecule. We have p orbital or double bonds here, 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 and here. So draw p orbitals on those carbons. Okay, we also have a carbocation at the end of the chain right here, so we'll draw a p orbital on that carbon. What you should immediately spot is that there's no place where you have 3 p orbitals in a row with no breaks. So we have a carbon right here that breaks up the row of p orbitals, a carbon right here that breaks up the p orbitals. So since there's not 3 or more in a row, there's no delocalization, and this is not conjugated.